welcome to a lecture class on a unit, design and analysis of experiments from the School of Pure and Applied Sciences and Department of Physical and Mathematical Sciences. My name is Timothy Kafue, the presenter. The unit is BMA4202, design and analysis of experiments. So the purpose of this, or the aim of this, the objective of this unit is to equip students, equip learners with skills of using appropriate methods, and finally, report on the research question. At hand, usually, research studies may be classified research studies may be classified as observational studies, and 2, experimental studies. Under observational studies, the researcher does not manipulate or has got no influence over the factors that affect the phenomenon under study. That is, data is collected without any attempt to manipulate it. Under observational studies, data is collected without any attempt to manipulate outcome. So we just observe the situation as it is, we correct the data and record it, and then work out or determine the outcome without influencing of the factors that affect the phenomenon under study. Well, in experimental studies, the researcher controls the input variables or factors the observational studies, one may just collect, say, a sample or 3 samples of fish from 3 different locations in the sea or in the ocean or in a water pool, and then weigh the fish to determine their maybe average weight, and then compare the 2 regions or the 3 regions that we have sampled by taking the samples of each. Or the researcher may also want to know the performance of students maybe in 3 different schools without putting the input of teaching. That is what we are calling observational studies. You just observe without influencing the factors that are affecting the outcome. But in experimental studies, one may want to feed the fish at 3 different locations within the pool or in different pools, and then see or determine the effect of the various types of nutrients that they were fed with. So in that case, we see we are influencing the outcome of the weight of the fish by determining what they are feeding on. But in the observational study, we are just getting into the pool, obtaining the fish, and then getting their average weight. That is what we call observational studies and experimental studies. In experimental study, we say we manipulate the factors or we control the factors that affect the outcome of the intended research. We are giving examples about how we do that. So we can even grow plants in 3 different plots and then apply different fertilizers to see the effect of the fertilizers. So the levels even of the fertilizers applied is manipulated. So the goal of the study is to find out the relationship between certain experimental factors and the outcome. The relationship between certain explanatory factors and the response variable. Yes, here we have 2 terms, that is explanatory factors and the response variable. Explanatory variables are those variables that influence the income. We also refer to them as input or independent factors. Say, for example, we want to conduct an experiment on the best combination of nutrients that will give us faster growth in chicken. Then we shall prepare diets with certain amounts of protein, carbohydrates, and other nutrients necessary for growth. And those ones are the ones that we are referring to as explanatory variables. So the response variable is the ultimate weight of the chicken, or the growth, the ultimate of the growth outcome after we have conducted the experiment. So an experimental study, which will be the core of this unit, experimental study, tests whether there is cause and effect. Test whether there is a cause and effect relationship between explanatory variables and the response. And the response variable. Well, in observational studies, test whether there is an association between explanatory variables and response variable. Tests whether there is an association between explanatory variables and response. So what is an experiment? An experiment is simply a series of tests in which changes are made in explanatory variables with the aim of determining how those explanatory variables influence the response, how those explanatory variables influence the response. So definitions. An experiment is a test or a series of tests in which changes are made in input. We have also referring to them as explanatory, all predictors, all independent variables. Input variables, so that reasons for change, in can be identified which affect output. Into bracket, we also call it dependent or response. Dependent or response variable. So an experiment is a test or a series of tests in which changes are made in input variables so that reasons for change can be identified which affect the output variable. So what is a response? So the response is what we actually measure or what we want to report after we have conducted a study, whether observational or experimental. So we define the term response variable. This is the variable. This is the variable whose distribution is of interest. This is the variable whose distribution is of interest, and it can be quantitative and can be quantitative, or that is either size, weight, height, time, etc. A quantitative variable is a variable that takes numerical values, or it can also be qualitative. AJ, yes, no, pass, fail, male, female, etc. A quantitative variable is simply a category or a class. Usually, the interest is in mean response. We are interested in mean response, the average. The reason for that is because if we are conducting a series of tests, several experiments, so we shall have various responses, but finally our interest is to take the average response, which we refer to as the mean response. Examples. Weight or mean weight of carrots planted Yes, so we shall have, our interest is on the mean weight, for example, of carrots planted under different conditions in a number of plots. So we could be imagining that we have, say, 10 plots, and we have some experimental conditions that we want to explore, maybe the amount of water, the fertilizer type, or even the temperature. And then we shall subject the plots and the plants within the plot to those different environmental conditions, and then we shall harvest. And then for each environmental condition, we shall require the average of the amount of carrots harvested from those plots where that particular environmental condition was applicable. So we say we can put this one in this form. Say we have 3 varieties of carrots like that, or fertilizers. Let these ones be fertilizers. We have 3 categories of fertilizers, A, B, C, and we have, say, the yield of carrots obtained from each of these plots where fertilizers were applied. The plots may be assumed to be of the same size, so that the only variable that is being observed here is the fertilizer itself, not the size of the plot. So maybe in, say, 10 plots with fertilizer A was applied, the mean yield per plot is maybe 20 kgs of carrot, and for similar size of plots, the mean yield of carrots where fertilizer B was applied is 30. So the variable under study here is the effect of the fertilizer, and which among the 3 has got the best output. Then we have explanatory variable. This is our response, mean response. This is the amount of carrots in kilograms obtained, average. Now, explanatory variable or variables are usually denoted by X, eyes like that, and they explain the variability in response. They explain variability in response. In our simple example above here, the explanatory variables are the effect of fertilizer A, B, and C. They are our X's. We have 3 of them. Others, not limited to fertilizers, could be, say, temperature, rainfall, or amount of wetness, variety of seed, etc. Those are the explanatory variables. Then what is a factor? A factor. A factor is simply a set of related treatments or characteristics or classifications used as an explanatory variable. A factor is a set of related treatments all classifications used as an explanatory variable. So in our example here, we could have even varied the levels of, or the amount of fertilizers applied per plot. So that the factor A, which is our fertilizer A, the input variable, the explanatory variable A, could be tested at different levels of its application, because maybe probably when at a certain level it reduces the harvest, and maybe we want to find the exact amounts or levels of fertilizer A can be applied. So we can also have the explanatory variable A observed at 3 or more different levels, 2 or more different levels. Then those ones are what we are calling a factor. So we are saying a factor is simply a set of related treatments or classifications used as explanatory variables. Then we have another term that we shall encounter in experiments is the treatment combination. Treatment combinations. Treatment combination. This, as the term suggests, is the combinations of all levels So if we have several factors or several explanatory variables at different levels, then the treatment combinations is simply the combination of the two explanatory variables at different levels, and then we want to find out how they influence the response. Then we have what we refer to as nuisance variables. These are other variables which influence response, but they are not of interest in this particular study or the study that the researcher is conducting. These are all other variables that influence the response, but they are not of interest in the study. So we are aware of the fact that even if we are trying to observe a particular fertilizer or any other factor, like other explanatory variable, there are other factors that may influence the outcome or the weight of the items that we are trying to measure. And that, or those other factors which we are not trying to study in our particular experiment, are what we are referring to as nuisance variables. For example, in the example of the plots and the carrots, we could be interested in determining the effect of the 3 types of fertilizers, but maybe there are other factors that will come into play, like the temperature of the environment under which the plots will be experimented, and that one is not the real cause of the study, and therefore we call it a nuisance factor. So we have what we also refer to as systematic bias. Systematic bias. This one occurs when treatments differ with respect to a nuisance variable. This happens when treatments differ with respect to nuisance variables, and we sometimes refer to them as confounding variables or confounders, also referred to as confounders. The real effect of the explanatory variable under study may be affected by these confounders or confounding factors, which we are referring to as the ones that bring about what we are referring to as the systematic bias. Then we have what we call experimental units. Experimental units. Experimental units. These are units or objects. These are objects or units that are independently assigned to specific experimental condition. Yeah, we can think of the experimental units as those plots take, for example, the example on carrots in plots. Suppose this is how the 3 fertilizers were applied, or even 2. Suppose we had 7 plots, 1, 2, 3, 4, 5, 6, 7 plots. And we are experimenting on 2 types of fertilizers on carrot yield. Each one of these plots is what we are calling to as experimental unit. Is an experimental unit that it is, e.g., a plot assigned treatment, say A, is what we refer to as an experimental unit, or a patient given a particular drug, or say a patient given drug, say C. That is an experimental unit. What are measurement units? Measurements the unit or object, this is the unit or object. This is the unit or the object on which a distinct measurement of response are made. A distinct measurement of response are made. And they are not necessarily the same as experimental units. Maybe in each of these, to make clear what a measurement unit is, maybe in these plots, each plot we had 50 or 10 plants of carrots or an n. Then each one of these plants and its weight is what we are referring to as a measurement unit. We shall measure the carrots and then add them together and then get the average to get the response for maybe plot 2. That is plot 1. That is what we refer to as a measurement unit. Then we have experimental error. Experimental error. Experimental error is simply variation among experimental units that have received the same experimental condition. This is the variation among experimental units that have received the same experimental conditions. So suppose we have two plots, plot 1 and 2. Fertilizer A was applied in both plots, and we have 10 plants or 5 plants per plot. And the mean weight for plot 2, is say 15 kgs, while the mean weight for plot 1 is say 15.2 kgs. Then the difference between the response in the two plots or experimental units, because we have applied the same conditions, is what we are calling experimental error. The difference between mu2 minus, or mu1 minus mu2 is what we are referring to as the experimental error. So the experimental error we have said is simply variation among experimental units. These are our two units, plot 1 and 2, and they have received the same experimental conditions. So the difference between yields, the mean yield in plot 1 and plot 2, is what we refer to as experimental error. So So we have three basic principles in experimentations, which we refer to as randomization, replication, and blocking. Three principles of experimentation. They are: one, randomization. This is the allocation of experimental units to the treatments at random or by chance. There is a known probabilistic way of assigning the treatments, say the fertilizers, to the plots. This is allocation of the experimental units to treatments at random or chance or using probability. Yes, random, chance, and probability, they mean the same. So if we want the outcome of an experiment to be really dependable upon the results of that response variable that we are trying to measure, then randomization is a good practice in designing experiments because it removes the possibility of introducing what we refer to as systematic error. Say, for example, we have, say, 5 plots or 10 plots or a number of plots on a lad with an orientation of XY like that, and we have 2 fertilizers we want to apply to the plots with the intent of determining which of the 2 fertilizers is good in terms of cultivation of a particular variety. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, let us make them 10. 10 like that. We want to compare the 2 fertilizers A and B. Compare. A and B in terms of yields. Now, if there is a fertility gradient along the line XY, and suppose we allocate plot of fertilizer A to every other plot after B like that, then so now this is allocation which we are referring to as systematic because we have started with A followed by B and so forth. Now we are trying to imagine if there is a fertility plot along the line XY. If there is fertility gradient XY as follows. Suppose this is the X, Y, and this is fertility. Like that. Suppose there is a gradient as such. Then, meaning that as you move from X towards Y, the plots increase in fertility. Then it means that if A is the first, if the first plot is assigned fertilizer A, and then B as such, then finally the final plot will have B. B, every plot of, or every experimental unit that has been assigned fertilizer B has already have an advantage over fertilizer A. So the outcome of that kind of an experiment will be influenced by several other factors. So it is not only A and B which are being in comparison, but also the fertility, because it appears B has taken advantage because it lands on the plots that have got higher fertility as compared to A. So we refer to that one as fertility gradient. And then the issue is there has been no randomization in terms of allocating the treatments to the plots. So that gives undue advantage to fertilizer B in terms of yield as compared to A. So we conclude that even if the varieties are equivalent, or the fertilizers are equivalent, the fertilizers are equivalent, in plots with fertilizer B, in the plots which B was applied. So there is need to do randomization. Randomization is simply allocation of the treatment units to, or the treatments to experimental units using a known probabilistic method. So what we would have done to make it random in terms of allocating, we get, we use the known methods of obtaining random numbers, and then we can have two cards with numbers A and B of the same size, and then they are put in a basket, and then they are well shuffled, and then we pick a card, and if it happens that the card indicates A, then the first plot we put A, and if the second pick indicates A, we put, and so forth. So that way we shall have used a random method to reduce or to remove the systematic bias. So another example could be if we have a greenhouse with some plots, and then we want to do an experiment concerning the two fertilizers still, then we need to assign the treatments, the fertilizers, in such a way that there will be no bias of one fertilizer maybe landing on a more warm place than the other one. Example 2, for the need for randomization, a greenhouse has 12 plots on which plants of two varieties, A and B, are to be grown. And suppose we assign the varieties as follows. Suppose we assign the two varieties as follows. The two varieties as follows. This is the greenhouse, And we have the plots. Suppose we assigned all plots to the left-hand side to variety A, like that. This is not a random assignment of the treatment. It is systematic allocation. This is a systematic allocation which introduces bias, For us to get a randomized experiment, we need to allocate the treatments in a probabilistic way. So we resort to what we refer to as completely randomized design. The reason for this, it could be that maybe the source of the right is towards the right-hand side here. And this is our left-hand side of the greenhouse. This is our greenhouse. Then it means that all plots on which the variety B were applied experienced higher temperatures, so which might influence the output, either negatively or positively. So we need to avoid that by using what we call completely randomized design. Why do we need randomization? It tends to neutralize all the nuisance variables. Randomization tends to it induces statistical independence also among, it induces among experimental units. Yes, those are the two advantages of randomization. We require to do completely randomized design so that the treatments are not allocated in a systematic way, so that we neutralize the effects of nuisance variables and also induce statistical independence among the experimental units. So these two varieties could be assigned in such a way that for a CRD, the same greenhouse, using probabilistic method, we could have the treatments arranged we could have BB and then AA and then say A, BB and then AA, BB. That way, the two varieties have been evenly allocated into all sides of the greenhouse, and that one will reduce the effect of the nuisance variables and also will induce what we are referring to as statistical dependence among the experimental units. What is replication? Replication is another attribute of a good experiment. Replication is simply a repetition of a whole or a complete set of experiments. A replication, this is repeating experimental learns one entire set. Experimental conditions is repeated using additional similar, using additional and similar. Independent yes, for us to get a good mean response, we need to replicate an experiment so that replication allows estimation of the experimental error, without which treatment differences cannot be concluded or inferred. Advantages of replication. Replication, we have simply said it is simply repeating of an entire experimental run. If we have conducted an experiment, we can repeat the same experiment and then observe the response, and then that way it helps us to have a firm conviction of the response value that we had obtained. So advantage one, allows estimation of the experimental error, without which treatment difference cannot be inferred. Number two, it also increases precision. Replication increases precision or power. Or power of the experiment. There is a difference between replication and what we also refer to as subsampling or pseudo replication. We note the term subsampling, which we may encounter in experiments, subsampling, or known as pseudo replication. This is taking of multiple measurements per experimental unit. This is taking of multiple measurements per experimental unit. Remember, we said that a plot is an experimental unit. So within each plot, we could have planted 50 or 10 plants. That is what we are referring to as subsampling or pseudo-replication. This pseudo-replication has got the advantage of reducing the measurement errors. It reduces measurement error in characterizing the response at experimental unit level. The advantage, instead of having just a single plant, in every experimental unit we have 50 or 100. The advantage of this subsampling is that it reduces measurement error, measurement errors in so suppose in a plot, this is a plot in which a treatment A was applied, and suppose our interest is to measure the height of the plants, and suppose we have, say, 10 plants. The instrument that we shall use to get the height of the plants, there is always an error in either reading or even the instrument itself. The person who is taking the measurement, if you have two different persons taking the same measurement for a single plant, it is highly unlikely that they are going to report the same height. Say, for example, if the first person says it is 10.1 centimeters, the next person may even find 9.9 centimeters. This is what we refer to as measurement error. And the reason for subsampling or pseudo-replication is to make sure that once we have introduced that measurement error from either the measuring instrument or the individuals taking out the measurements, then when we take the averages, it reduces the experimental error, or it allows it off, because in one plant we may have an overreading, and the other one we may have an underreading, and therefore the subsampling takes care of that. Suppose we randomize plots in a crop row so that we have some treatments. We want to do some expounding on the issue of subsampling. Subsampling. So suppose we randomize plots in crop row to two treatments. As follows: A, B, B. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 plots, and the treatments are completely randomized as such. And we measure the size of all the 10 plants in each plot. Suppose there are 10 plants per plot, where each treatment has been applied. Where each treatment has been applied. Say we have 10 plots. We have 10 plots. The plots are 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we have 10 plants per plot, so we have 100 plants. In total, we have 100 plants. And the plants are applied in 5 plots of treatment A and 5 plots of treatment B. Plots with treatment A are 1, 2, 3, 4, 5. So there are 50 plants for each experimental treatment, for each treatment A and B. So what is our experimental unit. The experimental unit, as usual, is simply the plot, and the 50 measurements per plot is what we are referring to as subsampling or pseudo-replication. A, we have 50 measurements per plot or per experimental condition. And B, we have 5 plots. This one, we are calling them experimental units. And there are 50 measurements. The 50 measurements are what we call the measurement units, and the 5 plots are what we are referring to as the experimental unit. So the sample size per treatment determines our power to statistically distinguish between the varieties A and B. That is 50. The sample size per treatment is 50. So there are 10 plants per plot, and there are 5 plots. So we have 50 treatments. We have the sample size is 50, and we are seeing that this sample size per treatment determines our power. Distinguish between varieties A and B. So we have, in this simple example, we have identified what is the experimental unit, what is the idea behind subsampling or pseudo-replication, and then we have also listed the importance of subsampling because it increases the sample size and therefore helps us to determine our power to statistically distinguish between the varieties A and B. What determines or what informs replication? Replication may be affected by several factors. Experimental materials, in terms of either if the experiment is being conducted in a laboratory, we may have a limited number of incubators. So even if we wanted to do replication, it is hampered by the lack of the many incubators. It could be also a time factor, and there are quite a number of factors that usually limit or may limit replication, which we have seen it is a good practice because it helps us to determine the experimental error. So factors that determine one, available resources. AG, cost, time, or even experimental materials. All these may harbor a replication. we look at other factors that may harbor replication. We have to size of the difference to be detected. 3, required significance level. Required significance level. And finally, the number of treatments. The number of treatments. If the treatments are so many, then the experiment may get out of hand because we shall be conducting so many tests, and therefore this could be the limiting factors of replication. But overall, replication is key in experimentation. So that practice of experimentation is broking. Broking is important because it helps us detect treatment differences. We would like the experimental units to be similar or very homogeneous as much as possible. We know that if we conduct a particular experiment today, maybe in a laboratory, if we repeat that experiment, say, in a few hours' time, the results may be different, maybe because of the exposure of the reagents to the atmosphere. If we are still using the same reagent, it could have absorbed some water, and therefore broking is key in experimental designs. So we say that to detect treatment differences, we would like the experimental units. We prefer the experimental units to be as homogeneous as possible, or uniform. Homogeneous is uniformity, except for the treatment received. Except for the treatment received. This is important because if we are to report on the outcome of an experiment, then we would want the experimental units or the objects on which the experiments were applied to have had similar characteristics as much as possible. So the idea of blocking is to divide these experimental units into homogeneous groups or subgroups within which treatments are observed. The treatment comparison can be made between similar units in the same block. This reduces experimental error and increases the precision. So when we apply treatments to units which are as homogeneous as possible, it helps us to reduce, it helps us to compare the treatments in the first place, and also it helps us to reduce the experimental error and increases the precision of the experiment. So advantages of blocking. which have now known to be homogeneous within each. So it helps us in determining the effect or the comparison, the treatment effects on the subjects, which have been now known to be homogeneous. So we now can compare the treatment because we have ruled other factors, other nuisance factors that maybe if we are trying to find out what is the opinion or political opinion of a group of people, we need to get that group of people maybe having similar life conditions. So there may be the influence of the locality within which a person lives. Say, for example, if you sample people from different estates, say a slum, and say another locality like, say, middle class locality. Their political opinion may differ simply because of their incomes. And therefore, if we want to find a political opinion clearly, we need to have sampled similar group of persons. Maybe we sample from a particular slum A and another slum B. Then we shall have an independence of the influence of the class or status to their political opinion, and therefore that is a good practice because it helps us to distinguish between the treatments when we know we are sampling from the same group. So the other issue of the other advantage of blocking, it helps the treatment comparisons and also reduces experimental error and increases precision. And increases precision of experiment. So even when we are applying it, say for example, in a large field, plots far behind, or if we have a farm on which we have several plots, and the farm extends very far, then maybe extreme plots on one side may have some effect that require to be blocked so that its influence on the outcome is not reflected. I want to give a small example on why we need to do some blocking and how we do it when we have a large piece of land and maybe we have several experimental materials or treatments that we want to apply, and then how do we come up with the blocks. And this is beneficial compared to CRD, beneficial compared to CRD. But if we have a known source, but if we have a known source of variability. We have a known source of variability, Kj, soil texture, etc., or something else other than that, or temperature, soil texture, temperature, etc. Then there is likely gradient characteristic. There is likely gradient characteristic that requires blocking of the plots, making blocking worthwhile. Example, making blocking worthwhile. We want to do a small, so we are talking of the blocking gradient and then presence of some characteristic. Suppose this is our field. Suppose this is our field. And suppose there is high gradient here of a characteristic, high gradient and low, like that. And these are the plots or the inclination of the land. Then the way to block, if we had plots on one side of the higher side which has got maybe a soil texture of good characteristic or even high water content in the soil, that is moisture, then the orientation of the plots with respect to gradient should be as follows. We should have the first block and the second. This is our first block, second block, and third block. So that the plots on each block, these are the blocks, so that the plots on each block experience both high and low gradient of the characteristic in question. So the placement of the plots should be that way, and then we go ahead and do our experiment, because we shall have applied the treatments through along the blocks, and the blocks are such that they are experiencing high and low gradient of that particular characteristic, whether it is soil texture or water moisture, uniformly, making or reducing the or doing out with the confounding factors. A number of factors which create heterogeneity in experimental units, resulting to blocking or giving rise to the need to block as follows. 1, time. 2, region. This is season of the year. Region, as we have demonstrated about maybe the landscape on which the field where the experiments will be conducted is inclined. And number 3 is facilities. So, say for example, in multiple greenhouses or even labs, we could have some limited or items of yesteryears, and therefore they might tamper with the result. And then finally, if we are conducting a research and we have different personnel to do the work, then there is a difference in the personnel characteristics that is employed or hired to do the work. Personnel Yes, the personnel difference conducting the experiment. One person may have some inherent inabilities or shortcomings that makes maybe the measurements units to differ from another person, so we need to do the blocking. Block effects are assumed not to interact with the treatment effects. We note that block effects are assumed not to interact with treatment effects. That is, where a region or a block effect may raise the yield for all the varieties, we assume that the differences in mean yield between varieties are the same in each region. That is one, while a region, which we refer to as a block, effect may raise yield for all varieties. We assume that the differences, we assume that the differences in mean yield between varieties are the same. In each region. So we are saying that while block effect may raise yield for all varieties, we assume that the differences in mean yield between varieties are the same in each block. That is, if we have a block 1 and block 2, and we have two varieties, A and B, and this is block 2, A and B. If the yield for A here is, say, 20 kgs, and for B is, say, 30 kgs, and suppose the yield for A here is 10 kgs, and for this other one is 15 kgs, then we are saying that the difference in mean yield between varieties are the same in each region, the difference in mean yield. So we can clearly see that the effect of the block here, it has doubled, and here the effects have been halved, so that we are only comparing the effect of the treatments and not the blocks. That is why we have noted that block effects are assumed not to interact with the treatment effects. The blocks are independent of the treatment effects. And number 2, if each treatment occurs in each block, and that is usually the case, if each treatment occurs in each block once, This assumption must be indicated during analysis, during data analysis. Otherwise, the analysis is likely to be wrong if the violation of each treatment occurring once in each block is violated. Yeah, we are saying that if each treatment occurs once in each block, this assumption must be indicated during data analysis, because if it is violated, then the results the analysis is likely to be wrong. When this belong like that. So also, number 3, we note that treatments effects are expected to differ. Treatment effects are expected to differ across blocks. If the treatment effects are supposed to differ, if the treatment effects are expected to differ across blocks, then we should use greater than or equal to. Then we should use greater than or equal to. If there is some known reasons to believe or to make us believe that treatment effects are expected to differ across the blocks, then we should use greater than or equal to 2 replicates per block to cater for the differences within each block and consider whether the blocking factor is more appropriately considered to be a treatment. Consider the possibility of using blocks as treatment factors. Factorial experiments. We have what we refer to as factorial experiments. After we are through with the definitions of terms, then we look at another type of experiment, also known as closed experiments, referred to as closed experiments. Here, the interest may be in determining the effect of one factor at various levels in conjunction with another factor, so that we also explore the possibility of interactions of the factors, one at low and another one at a higher level, or even both of them when they are experimented at various levels. So we say that when more than one treatment factor is to be studied, when more than one treatment factor is to be studied. We prefer to study them in combination. Rather than separately. Rather than separately. Yes, we are trying to imagine, say, for example, we want to conduct an experiment where we have, say, just let's take a minimum of 2 factors. And those factors, they influence the process in such a way that there are different levels need to be studied. We might think of this one as, say, for example, when we want to conduct an experiment on ethanol production, we could be having temperature and the duration or the time and even the pH of the concentration of the molasses that we would want to find out what is the effect of all those 3 factors, say time, temperature, and the pH of the molasses. Then, instead of studying 1 factor at a time, we can study the 3 factors or even more than 3 factors at various levels. That is what we call a factorial experiment or closed experiment. Closed experiment. We give a small example. 2 varieties of wheat. 2 varieties of wheat, A1 and A2, are to be studied in terms of their yield in relation to application of a fertilizer. So we have 2 varieties, A1 and A2. And we also have a fertilizer that we want to apply at various levels. So we can denote 0 and B1 as no fertilizer applied. We have no fertilizer applied, and we have the fertilizer applied here, where B0, no fertilizer, and B1, fertilizer applied. So the 2 levels of the fertilizer is no fertilizer and the fertilizer has been applied. Then we would want to find out what is the effect of the variety A with no fertilizer, variety A with fertilizer, and then variety 2, A2 with no fertilizer, and variety A2 with fertilizer. This is an example of a closed experiment or a factorial experiment. We refer this design increases efficiency. This design of closed experiments increases efficiency of the experiment and allows detection. of interaction effects between factors. An interaction occurs when the effect of one treatment factor differs depending on the level at which the other treatment factor has been set. So we say that an interaction is said to have occurred when one treatment factor differs depending on the level at which usually we have either no effect of interaction, or two, we have a synergetic effect, or three, we have an antagonistic effect. If the response does not change when two factors are observed at various levels, then we have no effect, or there is no interaction between the two. But if yield or response increases when the two factors have been applied at the same time, then that is what we call synergetic effect. And when the response reduces when the two factors have been increased, then we call it antagonistic effect. We also have what we call balanced experiments. Sometimes it is not possible to apply all the treatments into all plots, but other times we have equal plots, and we have a number of plots, and we have the number of treatments, and every treatment can be applied in every plot. Then that is what we refer to as a balanced experiment. A balanced experiment is one in which a balanced experiment is one in which the replication is the same. Under each level of each experimental factor. That is a balanced experiment. Say we have 3 treatments, and we have each treatment applied to, or it is replicated 5 times, or it is observed on 5 subjects. Then that is what we refer to as a balanced experiment. Example: 3 treatments A, B, C, each replicated n times. So we have observations, we have treatments. Treatments A, B, C, and the observations are here 1, 2, 3, up to n. If we have such an experiment, then this is a balanced experiment. Each treatment is observed n times. That is a balanced experiment. Otherwise, the experiment will be unbalanced. Otherwise, the experiment is unbalanced. We can have an unbalanced experiment, like say treatments here still, A, B, C, and then observations. Say we have, say, A, B, C, A or D, E, F, G, H, and say, for example, I, J. So treatment A has been replicated 3 times, or it has been observed on 3 experimental units, while treatment B has been observed on 1, 2, 3, 4, 5, while treatment C has been observed on 2. So making 10 observations, but A is observed 3 times, B 5, and this one 2 for 10 experiments. Suppose our n here was still 5, and we would have obtained 15 experiments. Yet this is a balanced experiment, but this one is not a balanced experiment because some treatments have been observed less number of times as compared to the other one or to the others. Balance is preferred in experiments subject to practical constraints. Since 1, it increases power of experiment, and 2, it simplifies statistical analysis. Simplifies statistical analysis. Another type of experiment is what we refer to as split plot experiments. Split plots experiments. Other split plot experiments, there is the use of multiple sizes of experimental units. This is the use of multiple sizes of experimental units. And it helps helps in adding flexibility, adding flexibility and allows investigation of additional factors. Those are the various types of experiments that and the practices of conducting experiments. When we talk of a split plot experiment, it is an experiment where the plots and the treatments for each treatment factor, they do not add up to all the plots being given the same treatment. Some plots receive treatment A, others do not receive a particular other treatment. So we have steps in designing an experiment. 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 We have to have the statement of the objective, what do we want to achieve in our experiment. We must state, or we must have the statement of the objective or objectives. Then we identify the sources of variation. So the question is, what are the exploratory variables that causes or that affects the response variable? So when we talk of identifying the sources of variation, we talk of one, selecting the treatment factors and their levels, selecting the treatment factors and their levels, Two, selection of experimental units and measurement units. Two, selection of experimental units. How are the treatments going to be applied, or what will be the experimental unit? Selection of experimental units and the measurement units. What are we going to measure and what do we use to measure? Measurement units. Then finally, or the third point, with selection of the blocking factor, selection of the blocking factors. With those ones in mind, then we are ready to look at how we do experiments. So when we talk of selection of experimental design, an experimental design, it is basically what we have already discussed. We have talked of a balanced design, a completely randomized design, an incomplete block design, and so forth. Incomplete meaning that not every treatment is applied to every plot or experimental unit. So we are talking of selection of experimental design, whether it is CRD, completely randomized design, or randomized complete block design, or balanced incomplete block design, etc. Then consideration of the data to be collected, what variables and how are they to be measured. We run a pilot experiment. We outline the statistical analysis and choice of the number of replications, then conduct the experiment, and then finally we report. Those are the steps that are necessary in designing experiments. In our next lesson, or in the next lesson thereafter, we shall look at the structures of experimental designs and the various types of analysis that exist. We have a one-way, a multi-way, and we have the analysis of variance as a method of analyzing the cell model effects or the random factor effects structures, which will be covered in our next lesson.
These televised lectures supplement our robust online learning going on our MKU online platform. You can view more on our televised lectures via our online platform. We are in a digital era, and Mount Kenya University knows this. The following are the steps to follow so as to complete your online application. Download the application form from the website www.mku.ac.ke. Attach copies of your academic certificates and ID. Pay the application fees via M-Pesa pay bill number 270988. Your ID is the account number. 2,000 shillings is the charge for a postgraduate. You can also deposit in the bank accounts provided on the website. Then email all the above to apply@mku.ac.ke.